In this lesson, we're going to specifically look at this force of friction and describe in a bit more detail how friction actually works and how we begin to deal with friction in systems where friction does act on the object. So a contact force that resists motion or potential motion, we usually describe this as friction. Usually I would say friction is a force that's a result of the physical contact of one object with another object, and that you're trying to push those two surfaces across one another or past one another. There are two main types of friction that we deal with. One of them is what we call static friction, and the other one is what we call kinetic friction. The word static, whenever you see that word, usually means stationary. The word kinetic usually refers to motion. So in static friction, the two surfaces are not moving with respect to one another. This doesn't necessarily mean that the object or two objects are not moving. It just means with respect to one another, those surfaces are not sliding past one another. The second type is kinetic friction. In this type of friction, those two surfaces are moving with respect to one another. So let's kind of look at how this actually works and look at this in more detail and where the difference between static and kinetic friction, or where that line is when static friction starts to become kinetic friction. How hard do you have to push something before it starts to slide across a surface? So here we have a graph, and this graph has two different forces on it. One is the force that you're applying to an object, and the other one is the frictional force acting on the object. So think of this as a box that's sitting on a floor, and you're trying to push the box across the floor. The applied force on the x-axis is how hard you push on the box. The frictional force is what is the force due to friction that's preventing the box from moving or resisting the motion of the box. You notice that there's this dashed line up and down kind of midway through the graph where it says instant of motion. This is the point where you've pushed the block hard enough that the block starts to move. So a few things to point out about this graph is on the left-hand side of this line, we have static friction. What this means is that this is before the object starts to move. So as I increase the applied force, at some point the object is going to start sliding across the surface. And what happens is the static frictional force increases as the applied force increases. We can actually say one more step, or one more thing about this. If the object isn't moving, these two forces have to be equal in opposite direction. This also indicates that there's a maximum value for the static frictional force, but that it could be any value below that depending upon what the applied force is. And motion starts when I apply a force that's larger than that maximum value to an object. On the kinetic side here, where it says dynamic, this is where this box is sliding across the surface. And after motion starts, the kinetic frictional force remains almost constant and is not dependent upon the applied force. Doesn't matter how hard I push the object, there's a constant frictional force acting on the block in this case. So how can we begin to mathematically describe these facts about friction, or these things that we know are true about friction? Well, the first thing we want to do is we want to break up what's happening into static friction and kinetic friction. Are the two surfaces stationary with respect to one another, or are the surfaces sliding past one another? If the surfaces are sliding past one another, we go to the bottom of my list for kinetic friction, and here I have the frictional force F is equal to some number that we call the coefficient of friction. It's this Greek letter mu times the normal force. This is the way you calculate kinetic frictional force. It doesn't matter how hard you're pushing on it. This is the kinetic frictional force. It's only dependent on the normal force. Static friction, what the coefficient of static friction tells you is really what the maximum value of that frictional force is. So we can use that formula to determine what is the largest possible value for static frictional force. Most of the time, if I'm dealing with static friction, I will probably need to do an equilibrium problem because the sum of all the forces on the object is zero if the object is at rest. So this value, or this Greek letter mu, is what we call the coefficient of friction. And really what the coefficient of friction is it's how do we relate the normal force to the frictional force. So let's look at an example problem. Here I have a 10 kilogram block that's going to slide down a ramp at a constant velocity. And I know the coefficient of kinetic friction between the block and the ramp is 0.4. And I want to know what is the angle of the ramp, theta. So first thing to point out, sliding at a constant velocity, this is an equilibrium problem, that the sum of all the forces acting in the block will be 0. So I'm going to use the same techniques that I used in equilibrium to solve this problem. I'm going to draw my free body diagram. I have gravity or weight pushing downward. I have the normal force perpendicular to the surface, and I have friction in the direction up the ramp. I could break up gravity into its x and y components. I could say the x component is going to be related to weight times sine of theta, and the y component is going to be equal to weight times cosine of theta. So next thing I'm going to do is I'm going to say sum of forces in the x direction is 0, sum of forces in the y direction is 0. Moving at a constant velocity, the net force has to be 0. And so I'm going to make the x direction the direction up the ramp, and the y direction perpendicular to the ramp, kind of like I've done with all ramp problems at this point. And so I could say the frictional force minus the x component of weight is equal to 0. The normal force minus the y component of weight is equal to 0. And so I could say friction minus mg sine of theta is 0. Normal force minus mg sine of or cosine of theta is 0. So here we get these two expressions, and this is really the exact same two expressions we had back in, I don't remember this problem, 3-2 or 3-3. We had the block sitting on the angled ramp, that the frictional force is mg sine of theta, and the normal force is mg cosine of theta. Now there is a relationship between the frictional force and the normal force that I can make use of, and since I know the coefficient of kinetic friction, I know that these two are related to one another. That I could say the coefficient of kinetic friction 0.4 times the normal force is equal to the frictional force. This becomes helpful because then I could say that over on my equation on the left, that coefficient of friction times normal force is equal to mg sine of theta, and I could then plug in what the normal force is, mg cosine of theta, and get coefficient of friction mg cosine of theta is equal to mg sine theta. Now if I look at this algebraically, the first thing that probably you should see is the mg's are going to cancel, and so I'm going to divide both sides by mg times cosine of theta to get rid of the mg's. The other thing, or the other reason why I divided by the cosine of theta is that sine of theta divided by cosine of theta, we actually have a trig identity for those. The sine divided by cosine is equal to tangent. And so the coefficient of kinetic friction is equal to tangent of the angle, so I could take inverse tangent of my coefficient of kinetic friction and get what the angle of the ramp is, 21.8 degrees. So there we go, we calculated the angle of the ramp. We could also go one step further and figure out if the coefficient of static friction was something different, we could maybe figure out what is the angle of the ramp where the block starts to slide down the ramp. Similar type of process if we're doing a static frictional problem. So that's another look at friction and how friction can be used to solve problems, and another way to begin to consider friction.